Hello, my name's Jeff Schmitz, and I'm here to convince you that there wasn't a Big Bang, that we have a steady state universe. So, what do I mean by that? Well, think about the Big Bang. You start with the Big Bang, you have this incredibly dense thing that makes up all the universe. It expands at first at an incredible rate, and it keeps on expanding, and it forms the universe that we know. And that's a very clear start to time that explains the redshift that we see and a whole bunch of other issues that it solves. But I'm here to tell you that there's another way of thinking in the universe that doesn't require a Big Bang, that explains all these things and actually explains some of these things better than what the Big Bang has. So there's definitely redshift. We see distant galaxies and they definitely have Doppler redshift to them. We look at the cosmic microwave background radiation, and that's definitely due to redshifting. But there's another way of having redshift. Instead of something going away from you, you can have gravity. Gravity can cause redshifting, and it's something that we see all the time. We look at the sun, and we see that it has a redshift due to its gravity. We have satellites that are going around the Earth that the Earth is redshifted in comparison to these satellites that are further away from the Earth's gravitational potential well. The Big Bang, you have a definite start. Well, how can you have a definite start if we have the steady state universe that isn't expanding, just stays like it is? How can we have a start and end? I'm going to try to explain that. And I feel that the steady state universe fits the data that we have better than the Big Bang. So, roughly, we have this redshift of a factor of 1,100 that we see from cosmic background radiation. If we look at redshift due to a point mass, just like I was talking about before with the sun and the earth and all these other things, you have a formula for that. But we're not looking at that. What we're looking at in this particular redshift is due to the universe itself. That we look 14 billion light years away at something that was 14 billion years ago. And we have a denser universe at that time. Not radically denser, but a slightly denser universe. And if we work those out, that we get this sheet. So if we think of this as this shell that's expanding out, then this shell has a area density of 9 times 10 to the negative 6 meters kilograms per meter squared. Cosmic background radiation has an energy density of 4.17 times 10 to the negative 14th joules per meter cubed. So that would make this the shell needed for this redshift at 1.9 million light years. So that's something that's not ridiculously big in comparison to billions of light years. And so these numbers are something that, at least roughly, seems possible. So the density in the universe is around 9 times 10 to the negative 27th kilograms per meter cubed. Density of cosmic background radiation, the number I got looked up is that 4.17 times 10 to the negative 14th. And then multiply that, etc. And we get to the amount of mass that's converted to make this is about 5.1 times 10 to the negative 28 kilograms per meter cubed. So we're talking about roughly around 10% of the mass of the original universe being converted into energy. That doesn't sound that extreme. Also, this isn't instantly happening at the shell. This is continuously happening. So what happens is that you have a universe that starts with mass and energy, and this mass gets converted into energy. Now there is some energy that's converted into mass, but overall, there's far more mass converted into energy than energy converted into mass. And so what happens is that we get less mass in the universe. As I said, it's happening right now as we speak. The sun is converting mass into energy. Mass is the only thing that creates gravity. You don't get gravity from photons. You only get gravity from mass. And so overall, the amount of gravity in the universe is decreasing with time. Not by much, but we're dealing with these huge distances. So we are currently in a lower gravitational redshift than in the past. And we look at distant objects, we see those objects from a past when there is more mass and greater gravitational redshift than what we have now on average. And so looking at an object, a planet, and it has redshift due to its mass, and work it out, and there's the force, inverse square law, etc. Now, if we look at this other thing where we're looking in the past and we see a denser, slightly more dense universe in the past than we do now, instead of being at the bottom of a potential well like we are on the planet Earth, broadly speaking, where we are is at the top of a potential hill. We look back in time and we see a denser universe. And of course, this doesn't happen instantly. This is happening very intensely at the beginning, but continuously happening now. And so one of the issues currently is that we have this change of rate of the redshift when we look at the Big Bang, and we're saying that the amount of redshift, essentially the universe is speeding up if we think of it as due to Doppler redshift of these galaxies going away from us. But if we look at it from gravity like this, then this explains that. That we're not going to we're going to see this rate of redshifting at first is a lot, but it's still continuous all the way until now. One of the things with an infinite universe and a Big Bang, it's a lot harder for us to think of an infinite universe with a Big Bang. But if we have a universe that we think of as infinite in volume and in time, then we're always talking about regions. Everything's regional. So we're not talking about the down the block or something like that, or a few light years away. Billions, trillions of light years is still regional. So it's a slightly different way of looking at things. So our current young region of the universe, that's where we're in, we got stars and they're converting matter into energy, so just like I was talking about before. After a while, you have a mature universe, or a mature region of the universe, and there you no longer have active stars. They've all gone through their life processes and all that's done after a long period of time. And then everything starts to cool down, and we have a bunch of black holes and white dwarfs and neutron stars, and they all start to cool down. And what happens is everything gets to be the same temperature, and we have this idea of heat death. And this was something that was around before the idea of the Big Bang, that's how the universe would end, and so it's heat death. And time gets less defined. we don't have energy to run a clock. It seems sort of simplistic, but if a clock or even a chemical process or anything that can measure time, we don't have anything that powers that. There's energy there, but there's no way of making that energy into something useful that can run a clock or a steam engine or whatever. So we get larger and larger regions that are undefined until our whole region that we care about is undefined in time. Time, in a sense, stops. But time starts again. How? Still working on that. But we had these sparks. Every so often, there's a place where just out of happenstance, time starts up. And then that time region expands out at the speed of light. And we have so what's needed to run a clock? You have a heat source, heat sink. If everything's the same temperature, like thermodynamics, things don't run. Or if you look at it with quantum mechanics, we have if we have very little change of energy between two things, then we get an increasingly large delta T, an uncertainty in time. So we have these sparks that somehow occur, and they go out in bubbles, and these bubbles go and intersect with each other, and we still have structure from the previous universe when time gets undefined totally, but still some of these structures like these black holes are still there. And when these time bubbles intersect with each other, we have densities that of material that hit each other, and we have these black holes that are nice to nucleate galaxies around. And so we have these voids where things aren't doing that, and when they intersect, then we get these filaments. So expanding versus steady state. So expanding universe is finite, or it's really hard to make it infinite. It might be possible. Requires energy for expansion, cannot explain the structure that we definitely see. Steady state is infinite. There's no need for this extra energy for this expansion. And we do have the structure from the previous universe. Here's a few other so I'm working on here. So the problem with the Big Bang, we see that the things are very uniformed, and we have this need for dark matter, need for dark energy. None of that is needed with this. Voids and other things like that, that that's explained with this. And so we look at the structure of our universe broadly, and we also don't see a the galaxies being closer to each other when we look further away. Now, if we are an expanding universe, galaxies should be closer to each other back in the old days than they are now. And we don't see that when we look at broadly the structure of our universe. We don't see these galaxies closer together than what we see now. Okay, and we see these voids and filaments. So, and the Hubble constant, I talked about that. So things to work on here with this is that nature of this undefined time. Does like light passing through an undefined region stop because everything else has stopped? I don't know. Maybe try and work on that. What's happening if we have uh, a a rogue planet that's there? Is it so undefined that it starts to break up? I don't know. The black holes, at least the larger ones, seem to hold up. What causes these sparks, I don't know. But also, there's something here that's cyclical because we go and we have these black holes. The smaller ones evaporate, the larger ones are still there. After a few cycles of this, you might end up with very large black holes and nothing else. And you imagine that even these large black holes of the next cycle, these supermassive ones might evaporate too. And then you start out with a whole blank universe again. And once again, this idea that everything's local, that this thing, a region of time being stopped, the region of supermassive black holes even evaporating and other stuff, if you went far enough that way or that way, you'd see a region that's